The fundamental entry to all laser materials processing is the question: what happens if electromagnetic radiation, laser radiation, hits a surface? Basically, there are three things that can happen. It can be reflected, it can be transmitted, or it can be absorbed. So consequently, this session is structured according to these three characteristics. We will start with some conditions on the surfaces, on real surfaces. Then we'll look at plane waves at interfaces, so the condition of what happens at the interface to the electromagnetic field. Then we will look at the amplitudes of reflection and transmission, the reflectance and transmittance. Then we will discuss what is called the Brewster effect, a very special absorption at a specific angle of incidence. And last not least, in the outlook, we'll take a look at the absorption, the definition of the complex index of refraction. Looking at ideal surfaces, usually we have the case that we have a perfectly straight, leveled interface between the incoming laser radiation and the medium to which we focus the radiation, and we will have very clear geometries in terms of reflectivity and absorptivity and transmission. In reality, surfaces look more like this, so we will have a direct part of reflection. So yes, a lot of the radiation will be reflected according to the ideal situation. However, we will have scattering due to the roughness of the surface. Sometimes we have periodically structured surfaces. Then, of course, we get periodically modulated reflectivity. In terms of application like welding, deep penetration welding, when we form keyholes, we will have multiple reflection in the laser-induced surface geometry. Sometimes we use coatings, and in these coatings we will have multiple reflection, like in a Fabry-Perot interferometer, in which we then will have interference of the reflected beams and thus a very specific wavelength filtering in terms of the reflected light. And sometimes we have high intensities, so we don't only get the what we call cold absorption processes or reflection processes, but we get the formation of a plasma, and in this plasma also we can have reflection, absorption or transmission. All in all, this equation actually represents the energy balance. So whatever comes in, imagine the intensity plotted here, will be either reflected to a certain fraction or it will be absorbed, and you already see here a exponential behavior of the absorptivity, and the last part of the radiation, of the incident radiation, will be transmitted. So absorption plus reflection plus transmission equals 1. To define a few things, we start with what we call the plane of incidence, which is formed by the vector which represents the normal of the surface and the incoming laser beam. This angle defines the area in which we use all our applications, and this is called the plane of incidence. At the interfaces, we can look at what happens now to the electromagnetic waves. Here you see the formulation of a simple propagating linear wave. E equals E incident naught times the exponential of I omega t minus kx. The same thing holds for the reflected electromagnetic wave here. So we denote that with ER for reflected and ET consequently for the transmitted part of the wave. We use complex amplitude vectors, which we will see later, because we need to take care of the phase changes at the interface depending on, as we will see, the orientation of the electromagnetic field. We will have phase jumps in the reflected beams. In general, we can say that the frequency is unchanged among all three parts of the beam, so the incoming laser frequency will be exactly the same to the reflected one and the transmitted one. however, which is not true for the wavelengths. That's where the index of refraction will come into play. And all three vectors will remain in the same plane, in the plane of incidence. Now, as you know or may know, the electrical field has one more property compared to the direction of propagation, and that is the orientation of the electromagnetic field vector E in terms of its polarization property. So if you take this into account, the following situation appears. We have a general orientation of the electric incident field, EI, and we split that up into a fraction in the direction of the plane of incidence and one perpendicular to the plane of incidence. So we call these IP for parallel and IS, this comes from the German senkrecht, meaning the perpendicular part of the electromagnetic field. So if we know the properties of these two components, we can construct any orientation of the electric field by just superposing the two components parallel and vertically perpendicular to the incident plane. If you look at the boundary condition, that is exactly at the interface between the medium number 1 and the medium number 2, then we learn from Maxwell's equations that we have two conditions for the magnetic and the electric field respectively. By looking at the magnetic field, we find that the dielectric displacement and the magnetic field are continuous, and that means that the vertical components, the components perpendicular to the surface, so in other words, in the direction of the surface vector n, are the same before and after entering the medium. So this is denoted here by n times b2 is the same as n times b1. So these vector components are exactly equal because over the change of the medium they are continuous. And the same thing holds for the electric field, but now not for the vertical parts of the electrical field, but for the components of the electric field parallel to the surface at which we have the change from medium 1 into medium 2. Taking into account these dependencies, we now can formulate the ratio of the reflected electromagnetic field with respect to the incident electric field, and that is what we call the reflection coefficient R. And correspondingly to the transmission coefficient is given by the ratio of the electric field transmitted with respect to the incident part of the electric field. For the reflection coefficient and the transmission coefficient, we now can calculate the dependence of the angle of incidence theta, and we end up with four formulas for the transmission coefficient and the reflection coefficient in the case of perpendicular orientation of the electric field, and the same thing for the transmission coefficient and the reflection coefficient for the case of parallel polarized radiation. In this special case, when we neglect absorption, we are just left with reflectance and transmittance. And if we look at the reflectance, which is just the square of the index of reflection, and if you look at the transmittance, which is defined again as the index of transmission squared. However, here we see that we have two more influence factors. Number one is the ratio of the indices of refraction and the angle of incidence. Of course, ultimately, energy conservation, if you have no absorption, then reads that the reflectance plus the transmittance equals 1. So everything which is reflected and transmitted needs to be the same as the incoming beam. Now, if you look at the graph, here's one more thing. If you look at a certain part of the beam which has a certain cross-section, then the reflected beam will look exactly the same. It will have the same cross-section, but the beam which is transmitted, as you can imagine, especially for larger angles of incidence, then the projection will be such that the diameter of the beam will be expanded, and the fact is that this expansion depends on the cosine of the angle of incidence, so this area grows with the cosine of the angle of incidence, and thus the energy density, so depending on the index of refraction ratio from incident area to transmitted area, we get this influence on the transmittance of the radiation. Now let's recall what we have so far. If you look at a surface and you come in with an electromagnetic wave, the electrical field will be oriented somehow perpendicular to the direction of propagation. Somehow meaning that parts of the electrical field will be perpendicular to the area of incidence, the plane of incidence. Others will be parallel, it will be in the plane. And now, if you imagine the two limiting cases, what happens when the incident beam hits the surface, in the case perpendicular polarized radiation, we will have, and intuitively you can see that probably there won't be a big dependence on what happens, because the electrical field is always, so to say, parallel in the surface. However, if the polarization is parallel to the incident beam, you will see that depending on the angle, the field vector will kind of stick into the surface and come out again. So there will be a pretty strong dependence expected for the angle of incidence for the polarization direction parallel to the incident plane. So what I just described by gesture, now you can see in a plot of the Fresnel equation which describe the dependence of reflectance and transmittance. Again, absorption is not included in this model. And you can see that for polarization perpendicular to the plane of incidence, which is S-polarized radiation, we have very little dependence on this angle of incidence. So it just changes from pretty high values. Metal reflect very good, at least for visible light, and that's what is assumed here as an example. You see that this changes very, very little. On the other hand, for the polarized light in the direction of the plane of incidence, you see a strong decline in reflectance up to very high angles, and then we come back to the value of 1 at an angle of incidence of 90 degrees. So again, if you approach 90 degrees by increasing the angle of incidence, then of course at 90 degrees we have a limiting case in which the radiation is simply on the surface, so reflectance is 1 and there's no transmittance. So all curves have to finally end in this point here, and depending on the index of refraction ratio at the interface, we get a starting point for the reflectance. As I said, for metals, now we can discuss an insulator. Think of glass. We usually have for visible light a value of about 4% of reflectance for vertical incidence. That is the value here, 4%. Now, and if you look at the S-polarized light, then of course you see a not very thrilling change, but somehow the curve needs to go up to 1, and that is the behavior of this part. If we look at the parallel polarized light, then we observe the same effect as for metals. We have an increase in transmission, a decrease in reflection. At a certain angle here, the value even goes to 0, and it is exactly 0. And then it increases back up to the value of the limit of grazing incidence with a reflectance of 1. A little addition, if you look at the complex values of these parameters, then you see for the reflection coefficient that depending on the polarization, we have a negative and a positive value, which simply represents for the complex notation that for the polarization parallel to the plane of incidence, we have no phase change, but for the S-polarized beam, we get a phase change of 180 degrees at the interface. We get a phase jump, as you may know it from mechanical waves which are reflected at surfaces. In order to make this a little more practical, we here listed a few values for typical index of refraction values and absorption values of different materials in the combination of different light wavelengths. So, for instance, if you look at a diamond at visible light, we see it has a very large index of refraction. Water is about 1.5 for visible light, and for diamonds we observe a value of 3. The absorption is negligible, as we know from diamonds. They are very nice and transparent. And if you look at the consequence for vertical incidence, you look at the reflectivity, we can calculate it, and it comes to a value of about 25%. Remember, glass was something like 4%. Now you know why diamonds are so desirable, because they reflect so intense and so they shine and they twinkle. That's why we like them so much. So if you look at other examples like glass, I already said that the value for the reflectance is about something like 4%. For a CO2 laser, however, in the far infrared at 10 micron wavelengths, we have strong absorption of the radiation, and consequently the reflection changes at zero incidence to about 25%. And as we are very familiar with for metals, in this case here at the example of aluminium, we have values of reflectance of the order of 90–95%. They are very shiny, they reflect the visible light. And if you look at values for solid or for liquid aluminium, we see that the values of index of refraction and index of absorption are in between 25 and 40, so relatively very high values. Coming back to the picture you have seen already, I now want to try to get a little more light into this effect here. So you see for insulators, at a certain angle, which we will call the Brewster angle, we will have practically no reflection. So all light is transmitted or absorbed, but nothing is reflected. In metals, it's a little different. In metals, we don't go really to zero, we go to low values, still a significant effect for the parallel polarized light. And the values for the angle at which this occurs is much higher, 85, 87, 88 degrees, depending on the metal. Now, how does that come about? There's a straightforward explanation to this, and this is sketched here in this picture on the left. If you look at a situation where the incident beam and the reflected beam, of course, are under the same angle with respect to the normal of the surface. However, the transmitted beam, the transmitted and absorbed beam, is in this case, in this special case sketched here, exactly perpendicular to the reflected beam. So if the transmitted beam and the reflected beam share an angle of 90 degrees, something very special happens. And this can be explained by the dipole radiation. Imagine the electrical field being perpendicular to the direction of propagation, of course also in the transmitted part of the beam. Then the electrons or the ions of the matter with which this electrical field interacts will oscillate in the direction of the stimulating electric field. So the electrons will move in the direction perpendicular to the direction of propagation of the light wave. So in this direction here. And now, if you look at the characteristic, how accelerated electrons radiate, you may know from antennas that when electrons are moved in this direction or in this orientation here, up and down, they will radiate perpendicular to this direction of motion, and only perpendicular to this direction of motion. There will be an intensity displayed here in these curves. It's like a donut if you think of a spherical geometric characteristic of emission. So if you look at the formula, you see it depends on the square of the angle under which the radiation is emitted. So here's a sine square of the angle. So at 90 degrees we have a maximum emission. Sine of 90 is 1. So perpendicular to the direction of motion of the electrons we will have the maximum emission. And sine of 0 is 0. So in the direction of motion we will have no emission at all. So as a consequence, this explains why we have these minima in reflection at specific angles which represent the case where the reflected beam is exactly perpendicular to the transmitted or absorbed beam in the medium. Some examples of how we can make use of that Brewster effect. In the left part of the picture you see a typical situation of a bore, a drilled bore, and in some industrial applications we want to harden the inner parts of that bore, so we somehow need to get into this bore under very, very small angles. And now, if you remember what we just learned, if we choose the Brewster angle, which is a very, very small angle compared to the direction of the bore, or a large angle compared to the angle of incidence, then we get the Brewster condition, so all the light will be absorbed very efficiently, even in otherwise very high reflective metals. Under perpendicular incidence we would have extreme reflection, but if you use the Brewster angle, everything will be absorbed. So here the condition of how to get into a bore and the vision or the condition of high absorptivity really match and get to coherent goals. And a similar application in all laser applications in cutting and welding immediately shows you it will depend quite a bit on the orientation of polarization, how this cutting curve or welding boundary layer between the cut and evaporated material and the base material will affect the absorption. Finally, we need to come back to the understanding that we discussed everything for the ideal situation of very plane surfaces. Remember, as I said in the very beginning, that usually we have rough surfaces, not ideal surfaces, so we will have parts of diffuse reflection. Usually we will have a mix of all. We will have some direct reflection and some diffuse reflection, so we have to be careful with these formulas for real surfaces. So as an outlook, we here see displayed an electric field entering some medium, and if the index of refraction in the medium is larger than in the vacuum, then we get a smaller wavelengths, and the wavelength scales with 1 over the index of refraction. Then when the wave again comes out of the medium, as sketched here, the original wavelengths again can be seen. On the way through this part of the medium, we see there is an absorption which took place, and this absorption scales with the exponential factor of an absorption index. This index is defined with respect to the electric field, as you can see here. And so the characteristics for what happens can be expressed by exact two properties of the material, which is the index of refraction and the absorption index. And that is why we combine those to a complex index of refraction. This n tilde is n minus I times kappa, kappa the absorption index. So for the intensity, we measure an exponential behavior of the loss of intensity along the transmission through the absorbing medium, and this is represented by alpha, alpha being the absorption coefficient, and it is connected to the absorption index by an exponential factor of 2, and this comes just from the square of the electric field to the intensity. Finally, the penetration depth of the radiation into a media then simply is 1 over the absorption coefficient alpha. So as a final aspect, we now see that it takes only 2 parameters to describe the full optical properties of a material in its reaction to radiation. And that is, in this case, the index of refraction and the index of absorption. You can define 5 of such parameter pairs in total, with which we can describe the nature of what happens if electromagnetic radiation hits a surface of a specific medium. And we only need 2 parameters of the medium to describe everything that happens with respect to reflection, absorption, and transmission. You already know these 2, the index of refraction and the absorption index, N and kappa. In the last slide, we also learned that the change of the wave number in the medium and the absorption coefficient can be taken, very similar to the ones above. However, then you may know from Maxwell equations the parameters of permittivity and electrical conductivity. From atomic absorption processes in plasmas or in metals, we know the plasma frequency and a collision frequency, which represents the dissipative, the energy loss, the absorption part of the process. And using ellipsometry, we can, just by analyzing the reflected part of a polarized incident beam, to identify the parameters of the material defining what happens in terms of absorption, transmission, and reflectance. So I think this is really fascinating, that if you ask the question, what happens if electromagnetic radiation hits a surface? It takes only 2 parameters of the material to define everything which is happening in terms of fractions of absorption, fractions of reflectivity, fraction of transmittance, change of polarization. All these things which can happen if we shine light on a surface are described by only 2 parameters, and we learned that there are 5 of such parameter pairs which we can use, and once you have 2 of such parameters, you can directly calculate the other 4 pairs immediately.